Welcome back. This is the second and hopefully the final segment for the last section in chapter 6. Wow, it's been a lot. But last time we talked about some very peculiar kinds of problems involving inverse trig functions. Now we're going to look at some that are a little bit more complex and a little more free form. So I'll just go ahead and switch right over here, and we can take a look at these problems. I may be able to get in as many as 6, but I'm not sure we really need all of them. So let me just adjust my image there a little bit. I think we're on page 3. Okay, so let's take a look at a problem. Again, these are just solved problems. So some of these, it's just about technique. So suppose that you have 3 arctangent of x equal to pi. So as I mentioned in the very beginning of this chapter, I said you really have to kind of have enough familiarity to know what kind of thing you're talking about here. This thing on the left is an angle, right? It's 3 times some specific angle too. And so the idea of just like slapping, like taking a trig function of both sides can cause problems because you don't have any formulas for triple angles. So right off the bat, if possible, you want to take the inverse trig function and isolate it, just like you would with a regular trig function. So we end up with arctan of x equal to pi over 3. And remember that when I was talking about taking a trig function of an inverse trig function, that if they were the same kind, like if we were to take tangent of the left, well, the tangent of an inverse tangent is never a problem. Unless for some reason x is not in the range of the trig function. Well, for tangent, you don't have any problems because x can take on any value. And generally, when there's a variable, you assume that it works, and then you see if some problem results. So what we're going to do here is we're going to take tangent of both sides. And this is going to be the strategy that we use on all these problems, is that we say we'll either take tangent, cosine, something of both sides, but they do get more complicated. This is actually a pretty simple problem. So when I do that, I end up with the tangent of the arctangent of x equal to the tangent of pi over 3. Now this can be evaluated. And again, like I said, most of the time when you see something that can be evaluated, you probably should. Over here, tangent, the arctangent of x, this just spits out x, and you end up with the tangent of pi over 3, which happens to be the square root of 3. And you can verify this if you want. You can stick it back into this equation and see what comes out. But I think you'll see that it works. Okay, so let's try another problem where maybe it's a little bit more challenging. It's similar. So let's take the arc cosine of x minus pi over 3 equal to pi over 6. Now I want to point something out. The book tends to do this a little bit, where they throw in things like this to make you kind of get confused about what this thing is. Remember, the inverse trig function of some ratio is an angle. So this thing inside here is not an angle, it's actually a ratio. And you can't just like throw it over to the other side or something like that. You have isolated the trig function, or the inverse trig function. So the process is to take the, not tangent, but cosine. I mean, you can do both, but it makes more sense to use the cosine. So when we take the cosine of the arc cosine of this kind of weird difference, and the other side will have cosine of pi over 6, well, we can evaluate pi over 6. That's going to be root 3 over 2. And when we take the cosine of the arc cosine, this just comes out. So we have x minus pi over 3 equal to root 3 over 2, which gives us the result that x is equal to pi over 3 plus square root of 3 over 2, which is kind of a weird sort of result, but so be it. But that kind of trickery pops up every once in a while. Now these are kind of the simple ones where there's only one inverse trig function, or maybe there's something that that can be handled pretty easily. But let me give you one where maybe they're a little bit mixed up. So let's take inverse secant of x equal to inverse cosecant of 2. Now you have to pause a second and say, is this, anytime you have something that involves two different inverse trig functions, you have to think about the quadrant. This is an angle in quadrant 1, right? Because that's in the range of inverse cosecant of a positive number. It's going to be quadrant 1. Inverse secant, it is possible for inverse secant to have a value in quadrant 1. And so we're going to be able to find an x that does this. We're just going to have to do some trickery, right? Now, if for some reason, if this was negative, like if we had inverse cosecant of -2, there is no solution to this problem, because this would be, inverse cosecant of -2 would be an angle in quadrant 4, but inverse secant doesn't have any values that spit out numbers in quadrant 4. So you'd have something that's just not possible. So you got to be a little careful there too, because you'll make mistakes if you don't just pause for a minute and say, is this even possible? It is certainly possible though. And so the strategy here is to say, okay, well, I'm going to take the secant of the inverse secant of x, and we know that this always works as long as that's in the range, and it will be. And now we have on the other side, we have the secant of the inverse cosecant of 2. And remember, these are the kind of things we dealt with in section, I believe it was 6.1, where we have these kind of mixed bag inverse trig function of one type with a trig function of another. And what I said is, if you're taking a trig function of an inverse trig function, this is an angle. And we need to basically draw the picture for that angle. We know it's an angle in quadrant 2, and we need to figure out what its x, y, and r is, value for a point out there on the ray. Now, cosecant is r over, r over x, r over y. And so we have a y value of 1, and r equals 2, so x must be equal to, I think if you do this right, you end up with maybe square root of 3. Okay, so it's going to be what? The square root of 2 squared minus 1 squared, which is just the square root of 3. So from this diagram now, if you want the secant of this angle, right? Because this little V shape, that is that angle. You're going to get it's not y over r. It'll actually be x over r. So we've got a square root of 3. Oh, sorry, not x over. That's the reverse. That's for cosine. It's r over x. So we've got 2 over root 3, which simplifies to 2 root 3 over 3, which we've seen several times. So on the left-hand side, we end up with x. On the right-hand side, using this diagram, you cannot get away from doing this. You simply have to draw the angle. Or, I guess you could sort of come up with the x, y, and r on your own, but this really is a very simple tool for that. So we have x equal to 2 root 3 over 3. And if you think about it, what angle is associated with a value of 2 root 3 over 3? Well, it happens to be a pi over 6 angle. And what value of cosecant is associated with this? Well, it happens also to be pi over 6. So if you plug them into your calculator, you'd see that they're both equal as well. So let's see, that's the first 3. The rest of them start to get a little bit harder. But they tend to use this same basic strategy where you pick one to take the trig function of both sides, and then you try to kind of figure out what to do with the other side. So here, let's consider inverse cotangent of x equal to inverse tangent of 4/3. Now, I can tell you the answer is 3/4. And here's why. We do have some trig identities for inverse trig functions. So we could do this sort of cheat way and say, this happens to equal inverse cotangent of the reciprocal of the number. And then we have inverse cotangent of x equal to 3/4, and we're done. But I want to caution you, because if this was another problem where we have the inverse tangent of -4/3, right? You've got to be careful. There isn't, remember we even spent, like, I can't remember which section it was, but we spent this whole space talking about what the piecewise function you'd have to write for inverse cotangent. And it turns out that this is not just simply inverse cotangent of 3/4 or -3/4. So here's where the clue comes in. This, you don't know what the value of x is. So inverse cotangent of x could be an angle in quadrant 1, or it could be an angle in quadrant 2, but not 3 or 4. If you look at inverse tangent of a negative argument, this will be an angle in quadrant 4. And so you have something that is not an angle in quadrant 4 equal to an angle in quadrant 4. This is not possible. So no solution. Right? And that sometimes does happen. But it's usually because, of these mismatches of quadrants or whatever else. And there's sometimes it really does help, especially when you've got some of these weird ones, to pause and think about, is this even a possible solution? Okay, so let's beef this up a little bit and look at one that has maybe a couple of functions. So how about inverse cosine of x plus 2 times the inverse sine of square root of 3/2 equal to pi/3. Okay, so if you're trying to find x, this looks harder than it really is, because you're wanting to say, oh gosh, that's a sum, and then you've also got a double angle and all kinds of other things, but yet this has a value to it, and we can just evaluate this. So inverse sine of root 3/2, well, that's pi/3, right? And then 2 times pi/3, so 2 times pi/3. Oh, sorry, I got the x there. 2 times pi/3 is going to be 2 pi/3. So now we have inverse cosine of x equal to, well, this is going to be -pi/3, right? Now pause a second, because there is this tendency to now want to take a cosine of both sides. And that would work under normal circumstances, except that it is not possible for inverse cosine to be equal to -pi/3. This is, regardless of the value of x, this is either undefined, or it is a number, or it is an angle in either quadrant 1 or quadrant 2. That's an angle in quadrant 4. And so it's not possible for them to be, for this equation to work. And so while it looks like you could continue with a solution and find one, there really is no solution. Okay? So that's a couple of tricky ones. But if we had changed just a couple of things about this problem, we could have gotten a solution. Like if you'd have changed the SIGN on that, I think you probably would have found a solution pretty easily. It would be, yeah, if you had minus, then, well, you know what, let me just go ahead and do that. So it doesn't take very long. So inverse cosine of x now minus 2 inverse sine of root 3 over 2 equal to pi over 3. Well, this is still just going to be pi over 3, and now it's negative 2 pi over 3. So we have inverse cosine of x minus 2 pi over 3 equal to pi over 3. And so when you move the 2/3 pi to the other side, you end up with the inverse cosine of x equal to pi. And that is allowed, right? So the you have to find the ratio that corresponds to that, or you can just take cosine of both sides, right? So cosine of inverse cosine of x is equal to the cosine of pi, and because we've already established that this is it's possible, we have x equal to, well, the cosine of pi is actually -1. So here we have just a simple change in sign results in something that is not possible, turns something that's not possible into something that is possible with a pretty easy solution. Okay, so I've got one more problem that I want to do, and this one is going to be the hardest problem that you will probably ever have to deal with, ever. And this is, let's see, section 6.4. Well, I say ever in this class probably. So consider this situation. We have inverse cosine of x minus inverse sine of x equal to pi. So ask yourself this first off, is it even possible? Yes, it's possible. And in fact, it might be kind of a trivial answer because here you have something that's in quadrant 1 or 2, and here you have something that's in quadrant 1 or 4, but with a negative sign. There's probably an angle that corresponds, one of these, there's some value of x probably negative that will result in this having a solution. So I can already just sort of surmise by looking at it that x is probably a negative number. But it doesn't really matter. The method would be kind of the same. Anytime you have a sum or a difference of inverse trig functions, you just want to take a look at it and say, is it even possible for it to equal the number on the right? It is. There is a certain combination in which you could get that. But then I want you to focus on the constant over here, because our strategy, we can't really separate these. We have to take a trig function of both sides sort of simultaneously, and we're going to end up with a difference, right? And we talked about those kinds of problems in section 6.1 right at the end. I said, hey, this is a really challenging sort of thing here. And that was when it had numbers. Now it's got letters in it. So the strategy here for me is to say, I want to do something with that pi so it becomes, when I take a trig function of pi, I want it to be 0. And usually the choice is, you may not be able to do that, but when you can, it's a really smart move. So I'm going to take the sine of both sides because the right-hand side will become 0. So I'm going to say, take sine of both sides. And again, the reason I picked sine as opposed to some other trig function is because sine of pi equals 0. That's the reason. Okay, so when I do that, I end up with an equation on the left, which is sine of the difference, inverse cosine of x minus the inverse sine of x equal to 0, right? So I got to pull out a difference identity here to be able to handle this side. That side's easy. It would have been more challenging if I had something else in there. So I have, for sine of a minus b, it is sine of the first thing, which is our inverse cosine of x, times cosine of the second thing, which is inverse sine of x, then minus sine of the second thing, which is inverse sine of x, times cosine of the first thing, which is this inverse cosine of x. And I think I got all the parentheses right. And of course, that's all equal to 0. Ran out of space there a little bit. So these two are easy, right? The sine of the inverse sine of x is just simply x. The cosine of the inverse cosine of x is just simply x. So this whole term reduces down to minus x squared, right? So I'm just going to kind of do a little bit of graphics here. This, including the SIG in the front, reduces down to minus x squared. Now, what about this over here? Well, we've already kind of surmised that x needs to be negative. And that's kind of critical, but I don't think it'll make that big of a difference. But let's start by drawing the this angle, right? So since we've established that that we're going to need something in quadrant 2, probably. I mean, I think we can just wing it. It turns out that you've got some things that are square roots. They get multiplied together. Everything else. This probably won't be as bad as I'm making it seem like. So let's start with this one. So if cosine, let's just try it in quadrant 1. Usually when you try something in the wrong choice of quadrant, you get something that tells you the value is negative. So it's not the end of the world. So for an angle in quadrant 1, there's a point on this terminal ray where the x value is equal to x, and the r value is equal to 1. So y is going to be equal to this really ugly square root of 1 minus x squared. And there's not really anything we can do to make that cleaner. So that's the y value. So this sine term right here becomes y over r, or simply the square root of 1 minus x squared. And it turns out that the other one's going to do basically the same thing. So let's assume that we're angle in quadrant 1. And in this case, it's not the x coordinate that's equal to x. It's actually the y coordinate, which is very confusing. But there's y equals x. Nutty. Now let's find out what x equals. So r again is 1. And again, we have that x is equal to the square root of the r value squared minus the y value, which happens to be x, which sounds really bizarre. I mean, I wish there was a way that we could put something on there to indicate that this is a coordinate and that's a variable. But sometimes you have to muddle your way through that. So again, the cosine of the inverse sine of this angle is the square root of 1 minus x squared. So both of these become the square root of 1 minus x squared. So let me just go ahead and move down here and actually write that. So I'll do it with a little different colored pen. So based on this diagram, based on this diagram alone, this transforms into square root of 1 minus x squared. And this one next to it does the same thing. Square root of 1 minus x squared. And then, of course, don't forget the minus x squared and what it's all equal to, which is 0. So when we simplify this, right, this is the square of a square root, you get 1 minus x squared minus x squared equal to 0. And so what we're left with is an equation that says that 2x squared is equal to 1, x squared is equal to 1/2. So x must be equal to plus or minus the square root of 2 over 2. Now, this makes me a little bit nervous because I'm not I'm not entirely certain that there's a solution that will equate to this minus term. And that comes from the fact that we made some assumptions about this, that this equation was defined, right? We said that this, whatever this angle is that's in here, or is going to work, right? And that right there alone could be false. I mean, we did this little investigation at the beginning to say X has got to be, probably got to be negative. And so being positive is going to be a problem. But let's just check. So if we take the positive root 2 over 2, well, the inverse cosine of positive root 2 over 2 is pi over 4. So we have pi over 4, and then the inverse sine is the same number, so it's pi over 4, but it's minus. Pi over 4 does not equal pi. So this positive branch will not work. Check the other one. So if we go the other way, we have negative root 2 over 2. Well, the inverse cosine of negative root 2 over 2 is actually an angle in quadrant 2, and it happens to be 3 pi over 4. And then the inverse sine of negative root 2 over 2 happens to be an angle in quadrant 4 with the negative SIGN and the reference angle pi over 4. So it's minus a negative pi over 4, minus a negative pi over 4, which happens to equal pi. And so that one checks. So our net result is that X is an element of the set that contains the negative square root of 2 over 2. And that's just foolishly complicated set notation. Okay, so this is a very challenging problem. It kind of brings everything together. And usually when I talk about this last problem, this is usually the last problem of what I consider to be the trigonometry. I just want you to think back to the first day of this class and realize how far you have come. So with that, I'm going to call it quits. There are 2 more sections that we'll talk about in chapter 7 that are about vectors, which are very specific applications, which might be a good change of pace. But I'll be seeing you around.